Okay, good afternoon, everyone. Today I'm gonna talk about a new chapter, just chapter 15. And chapter 15 is nothing but, more about the waves and then, the sound and light, which is waves as well. So as long as you are, you know, confident about the previous chapter, you will see you'll be fine, okay? And then there are two different type of wave models. And the first one is called transverse wave. That means, and then they have also have a we have a longitudinal wave. Transverse wave is a wave in which the particle in the medium move perpendicular. So the particle here, for the string wave is in the string itself, right? The string is moving up, down, while this wave itself moving horizontally, right? So then we call it transverse wave, right? And then which is a wave, the particle in the medium moves up perpendicular to the direction in which the wave travels. For this case, wave travels horizontally, the medium moves up, down, right? And then another type of a wave is called longitudinal, right? So the example of longitudinal wave is a spring, right? The spring, if you oscillate, your spring is moving back and forth. Spring itself is medium, right? And then also the wave itself is also travel horizontally. So then we call it longitudinal wave. The particle in the medium moves parallel to the direction in which the wave travels. And then waves, we'll talk more about wave on a string, right? This again is a transverse wave, right? And now a wave on a string is traveling to the right. So assuming the wave is traveling to the right, at this instant, the motion of a piece of a string marked with a dot, right? So the wave itself is traveling to the right. What does that mean? The whole string moves up and down, right? It seems like the wave crest is traveling to the right, but the actual point of the wave is not traveling horizontally. It only moves up, down. Okay, so the answer for this question is this point sometime later, because the wave is when the wave is traveling to the right, this position will go up, right? In other words, this is when t equals 0. 1 second later, this wave crossed will travel this much, right? And then the actual wave shape is something like this, right? And then this point is just here. Again, when the actual wave crest is traveling, the particle, which is the string, the portion of string, segment of string doesn't move horizontally. It will also only moves up and down, right? And then we have a sound wave, which is a longitudinal wave as well. So then now you see the compression is the disturbance that travels through the air. So now you have a air compression, and then you have a less air, and then somewhere here you have an air compression. So it's more like a spring is compressed here, and then you don't have a spring, a lot of spring here. So it's like here, right? So you have a compression, rare compression, right? Something like that. So the you see sound wave is also longitudinal wave. Mhm. And then speed of sound wave is 343 meter per second at 20 degrees. Even though this is at 20 degrees only, and then wave travels, at different speed as a function of a, temperature, but you can simply assume, sound wave velocity is a 340 meter per second, roughly, doesn't matter. And the speed of light is much faster than the speed of the sound. This is a 3 times a 10 to 8 meter per second. This is much faster than 340 meter per second, right? So basically that means this light travel, extremely fast. So then, in other words, whenever somebody turn on the light, you can immediately see the light, right? But if somebody generate a sound, you can hear this sound sometime later because it travels with a much slower speed. So, for example, this is one of the very famous question you will see. You know, during the thunderstorm, you will see a flash from a lightning, right? So then, whenever you see this lightning, because again, the speed of light is 3 times 10 to 8 meter per second. So that means in 1 second it traveled this much distance. So you see the light almost immediately. So whenever you see this light, so that is basically you can assume t equals 0 because you see almost immediately, or 0.00001 second. So it's a 0, right? But 8 seconds later, you hear the crack of the thunder. Why? Because once you have a thunderstorm here, they generate two waves. The first one is a light wave, and the second one is a sound wave. So then, assuming you're here, you will see the light wave almost immediately because of their fast speed. And then you will see sound wave because they travel much slower speed, right? So how far away did the lightning strike? So simply they travel 340 meters per second. So 8 seconds later, they travel this distance, right? So the answer is 2.7 kilometer, right? So because they roughly travel 340 meter per second, which is about 3 times 340 is about 1 kilogram, right? Kilometer, I'm sorry, right? So that means every 30 seconds you assume that thunderstorm is 1 kilometer away. Okay. So the next topic is much more complicated. I believe I briefly mentioned about this, but I'm not sure. So let's assume you have two different type of graphs. The first one is your y position, and then sometimes you have a wave function, right? So we use the cosine function, but we can also use the sine function. So let's use the sine function for this case, but basically the same idea. So then now, what is this? I know some of you who studied in the last chapter hard will say this is gotta be your period T. But I know also some of you who took a physics, in your high school, some of you probably say, oh, the distance between two crests, I heard this is lambda wavelengths. So what is the correct? The answer is correct. So the both answers are correct or both answers are wrong. Depends on what is your x-axis. If your x-axis is a distance, then this is lambda. If this your x-axis is time, that we used, this time axis last chapter, then that's a period. So basically you will see there will be two different type of waves. Position versus another position. And then position versus a time. And then you have a boom, 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 boom. And then you see the distance between these two crests is called lambda wavelength, which I will introduce later. And then if this is a position versus time graph, then we call this one periodicity. Okay, and I will explain briefly about the differences between these two graphs. And then next section, next lecture, will go more details. Okay. And then now you see, I will introduce a snapshot graph. Snapshot graph shows a wave's displacement as a function of a position at a single instant of time. So again, this is a position versus a position. So this is more like a, assuming you go beach and then you see wave, right, in the ocean. And then let's assume you take a photo. Then this is exactly what you're gonna see, right? Wave is moving this way, and then you take a photo. So the snapshot graph is because you take a photo. This is at a fixed time when you take a photo. So this is a exact physical position of each waves. Okay. So then of course the wave speed is moving v. So that means that this crest is traveling move with the velocity speed v, if you keep observing it. But again, snapshot graph is your position versus another position at a fixed time t. That's why it's called snapshot graph. Okay, so now let's assume we are interested in the Coke can, right? No, this wave here, right? And then sometime assuming the wave is traveling to the right, and then assuming you take another photo in a few seconds later, maybe 1 second later. And what you're gonna see is not this original wave, but the wave is traveling. Let's assume this is the original wave, the same as this one. I'm trying to draw the similar shape here, here, here. But this is the original wave. But sometime later, the seconds later, what it looks like, right? Because the wave is traveling this much from here to here. But the location of the Coke can is now here. Again, assuming you have a Coke can in the ocean, and then assuming there's no wind blowing horizontally, the horizontal position of the Coke can never change. It doesn't move horizontally. It only travels up and down. So this is a position of this blue Coke can at another fixed time t1, right? And then so again, as the wave moves, you can plot a sequence of a snapshot graph like successive frames from a video, right? So wave at a time t1, this is your first snapshot when t equal t1, and then wave will trouble, wave front will trouble actually, right? Wave crest, I mean, and then sometime later wave crest will trouble here. But again, the thing is, your Coke can, assuming it was initially here, it's not gonna trouble. Sometime later, it's a X position. Let's say this is a 2 meter from the origin. So then 2 meter from the origin, your Coke can position doesn't change. It's still here. Only height was initially maximum height, but now gets lower. And then here, later again, 2 meter height is here. Okay, so only is a vertical velocity position is changing while the wave crest or whole wave shape is traveling to the right. Of course, wave can travel to the left as well, right? And then next graph is history graph. So again, history graph, you take a graph position versus a time. And then now I told you the snapshot graph is what? The photo of a full wave, right? So then in your snapshot graph, every single snapshot, you will see a Coke can here, Coke can here, Coke can here. So one of the question you have is what if you're interested in the height of the Coke can as a function of time? That's the histogram. You are only interested in height of the CocoCan here as a function of time. So then, this is a position x1. So again, in other words, histogram, history graph, you observe a at a fixed position. In other words, you just observe CocoCan, right? You only observe CocoCan's height as a function of a time. So then, okay, this is your snapshot graph. Okay, my first snapshot when t equal t1, my second snapshot when t equal t2, my third snapshot here, my fourth snapshot, and then now you see when t equal t1, okay, my height is some positive y number, and then my position gets almost max, and then later, okay, my position gets lower, and then my position when t equal 4 is 0. So then if you convert this graph, so this is a set of a snapshot graph to one history graph as a function of time. Okay, I'm observing the same location, x1, and height was initially, okay, here. And sometime later, my height is here. And then sometime later, my height is here. And then my height is 0. So then you see, especially when the object is the wave is traveling to the right, you have a opposite shape. Because why? Because if the wave is traveling to the right, so this case we assume here this wave is traveling to the right, right? And then you are observing this height first, right? So that this wave is this wave is moving to the right. What you're gonna see is that this first, right? You will see this change first, right? So your height is increasing as a function of time. So that's why you will see, you basically have two different lines, right? One steeper line and the other one less steeper. But you will see this steeper part first. That's why if you convert, a snapshot graph of a wave moving to the right, you see this part first. And then you see this part later. It's a opposite here, right? So think about it very carefully about what I just said. It's very confusing, okay? And then now, okay, I can have one or two more, examples, and I will stop today's lecture. And I will want to ask you study this part very carefully, and then we will go, study more about, we'll go with more examples about this. Okay, so this is snapshot, right? At a fixed time t, right? So t1 is a wave pulse traveling to the right 1 meter per second. So this wave front is traveling 1 meter per second. So that means 1 second later, this pulse gotta be here. Another second later, this crest will be here. And 1 second later, this one will be here. Another second later, this will be here, right? So which graph below shows a wave pulse t equal -1? Physically, that's not possible. But in other words, that's 2 seconds before. So 2 seconds before, this will be here, right? And then this point gotta be here. So you just shift whole graph to the left 2 units, right? So the answer is A. And the second question I have is the graph below shows a snapshot again. So then this is Y versus X of a wave on a string that's moving to the right. You always have to see the direction as well very carefully, right? Because if it's moving to the right, you will see this part first. If it's moving to the left, you will see this part first, right? A point on the string is noted, right? So we are interested in this position, right? Which of the choices is the correct history graph? So you are basically converting, snapshot graph to history graph. So then now, history graph, again, what are you doing? You gotta observe one point, right? In other words, this is at a fixed position, right? So we're gonna observe this position only. And then what will happen? Because the wave is traveling to the right? This part will come this position, short time later, right? This will be here. And then sometime later, what happen? This will come here. So, when the wave is coming travel like this way, and then your height will be here. And then when this part comes here, your height will be here. So you will see this change first. So your height is changing with this along this straight line. And later your height will be changed along this line. So the answer is a yes, B, right? You will see this change first, nothing for the first few seconds, and then you will see this change, and then you will see this part, right? And then, yeah, let's do the one more last question. A graph below shows a history graph. Now it's you have a history of the motion of the one point of the string, and then again the wave is traveling to the right? And then which one is a correct snapshot graph of the motion of the string? So then now, again, this is a history graph. So then it means when you observe first, at a fixed position, then you will see this one. So initially you don't see any changes. So again, the wave is traveling to the right. So you must see nothing for the first few seconds. You see nothing changes, nothing changes, nothing changes, nothing changes. Okay, A, B, C, D makes sense. And later, what do you see? Oh, I see this height changes. Height is increasing, right? So then I should see increasing height. So then again, snapshot is traveling, your wave is traveling to the right? So you have to see height change, and then but the height must be positive, right? But this is you will see it's getting lower and getting lower, getting higher, getting lower, right? So I'm sorry. So your position is getting higher, right? So the answer is D, right? Why? So I'm sorry, I have to focus on this area, right? Sorry about that, right? Because you will see initially 0, 0, 0, 0, right? And the next time what you're gonna see, because the wave is traveling to the right? It's this area of the wave is what you wanna see next, right? So this corresponds to this, right? So your height must increase. So this is how it decrease, height increase, but not this much. Height decreasing, height increasing. So your answer is D. Okay, and then we'll talk more about these two waves, snapshot and history graph. But make sure how you convert these two graphs, okay, based on the examples I gave you. And I'll see you next time. Thank you. And then let me know whenever you have a question.